In this video, we will understand the concept of interference of waves from two separate sources. Now, broadly classified, sources of waves can be of two types. We have coherent sources and we have incoherent sources. Coherent sources are those which produce waves that have the same frequency and zero or constant phase difference. An example of coherent light in daily life is the laser. Lasers are extremely bright, but more importantly, all the light beams are coming at the same frequency and have the same phase relationship. Incoherent sources are those where there are multiple frequencies and multiple phase differences between the various waves. An example of this is the light bulb. We are going to use our previous knowledge of the superposition principle to understand how interference works. Now, as we learned earlier, the principle of superposition tells us that the resultant displacement produced by any number of waves meeting at a particular point is the vector sum of the displacements of all of these waves. And superposition can be defined in two ways, constructive and destructive. Constructive superposition is one in which the waves are in phase. Imagine that the crests of multiple waves are meeting at the same place and the troughs of multiple waves are also meeting at the same location. The crests would add into each other and the troughs would also subtract from each other. In essence, the height of the crests and the depth of the troughs would increase, thus the amplitude of the entire wave is increasing as a whole. In other words, you are constructing a larger wave by superimposing two separate waves, which is why we call it constructive interference. On the other hand, destructive superposition is one in which the waves are out of phase. So imagine if the crest of one wave is meeting the trough of the other wave. The displacements are in opposite directions, so when they add, they go to zero. So in destructive superposition, the net output becomes zero. The wave has zero height at that point. Now let us apply our understanding to a simple case where we have two sources creating waves in a medium. So here we have two dippers and they are producing two sets of waves, S1 and S2. As we dip these dippers again and again into the water, we have two wavefronts S1 and S2 which are moving forward in space, and these waves are being repeated again and again. Now, as these waves are traveling through space, they are interacting with the neighboring wave. So S1 is interacting with S2, or we can say that S2 is interacting with S1. And depending on the distance from the wave, and also depending at the point where we look at the interaction between these waves, if the waves are in constructive superposition, the height of the wave will increase, and if they are in destructive superposition, the height of the wave will decrease. So how do we know whether the waves are interfering constructively or destructively at any given point? Let's find out. So here we have the sources S1 and S2, and we want to know how these waves will interact at a point Q at some distance away from them. From this image, it is very clear that the two waves are not traveling the same distances to reach point Q. For example, if you were to draw the wave shapes traveling from S1 and S2 towards point Q, you notice that there is a difference in the number of wavelengths required to get to Q. S1 can reach there in 7 wavelengths, whereas Q is reaching there in 9 wavelengths. Now, because the difference between these two wavelengths is an integral number, we notice that when these two waves reach point Q, they are perfectly in phase. In other words, the crests of S1 and S2 are lined up and the troughs of S1 and S2 are also lined up. This is a case of constructive interference where the waves add up and the resulting wave becomes larger. What about the other case? Consider another point. So here we see that the difference between the path lengths, that is S1Q and S2Q, is equal to 2 lambda. So it is an integral multiple of the wavelength of these two waves. This means that when these waves meet at point Q, the crests will line up with each other, the troughs will also line up with each other, and the two waves will add each other constructively. So the wave becomes higher at point Q. Now consider a different case. What would happen if this was not the path difference between these two waves? In this particular case, we are concerned with how the waves will interact when they reach point R. Again, you will notice that the distances from S1 and S2 to R are not equal. For example, here you will notice that the distances are 9.75 lambda and 7.25 lambda, and the difference between these is not an integral multiple. The difference between them is 2.5 lambda. So here we have a path difference of 2.5 lambdas, and this is a case where we will notice that at point R, the crest of one wave will be interacting with the trough of the other wave. So here we are noticing a case of destructive interference. The net intensity of the wave at that point will be 0. But how do we express all this mathematically? Let's say we are dealing with two waves which are completely identical in every regard. So we have y1, that is a cos omega t, and y2, which is also a cos omega t. If these two waves are adding up perfectly or they are superposing constructively, then what we are getting is a new wave given by capital Y, which is equal to 2a cos omega t. Now, what is the relationship between the amplitude and the intensity of this wave? Well, we know that the intensity of a wave is proportional to the square of the amplitude. So in this case, for this particular wave, we have the intensity being proportional to the square of 2a. So we can say that the new intensity is proportional to 4a square. That is the square of 2a. Thus, we can say that with reference to the original wave, the intensity of the new wave is 4 times greater. Hence, there is a change in intensity by a factor of 4. Now, what is the condition for constructive interference? The condition is that the path length between the two waves, or the difference in the displacements of the two sources S1 and S2 from the point of interest, has to be a whole number multiple of the wavelength. So it has to be equal to n lambda, where n is some whole number. What about the intensity at the null point? Well, in this case, we are talking about the height of the wave at a point of perfectly destructive interference. In other words, the crest of one wave is meeting the trough of the other wave and they are cancelling each other out. So obviously, the intensity here will be equal to 0, which corresponds to the dark region if you are performing the same experiment with two sources of light. What is the condition for darkness? The condition for darkness is that the path length between these two sources has to be a multiple of n plus 0.5 lambda, where n is some whole number. So, if the difference between the two paths is equal to some whole number plus 0.5 multiplied by lambda, in that case, at that particular point, we will observe zero intensity or darkness. Now, how do we derive the phase relationship between these interfering wavefronts? Before, we had considered two waves which are perfectly identical. They had the same amplitude, they had the same frequency, and they had no phase difference. Let's consider a slightly more different case where we have two wavefronts, let's say they are y1 and y2, which have a constant phase difference of theta. So we have y2 is equal to a cos omega t plus theta. This is the constant phase difference between these two waves at any given point of time. Now, if we are to find out what is the result of superposing these waves, then we have a new wavefront, that is capital Y, which is equal to the addition of y1 and y2. So if we look at this, this is capital Y is equal to a cos omega t plus a cos omega t plus phi. We can use a trigonometric identity to come to the answer that the amplitude of the waves is equal to 2a times cos theta by 2. This implies that there is a dependence between the phase angle between the two waves and the amplitude of the wave after superposition at any given point within that region. Now let's summarize what we have learned so far.
Manorama Horizon. Learning made simple.